All right, we're getting closer and closer to wrapping up chapter two. If I'm not mistaken, this is the last section in chapter two, and we will be reviewing our next time together and then having a test on everything we've done in chapters one and two. Bear in mind that the test on chapters one and two is always one of the absolute easiest tests for this entire course. Okay, so I've got a number of really interesting misleading statistics and some out and out crazy statistics for you this morning. Here's an interesting one. We were enduring a recession in the early part of the 2000s, a minor recession compared to some that we've seen lately. And about 2003, Bush was president at the time, instituted a tax cut, and look what happened. Okay, payroll employment went up. So do we assume that the tax cut actually helped that many people get jobs? Right? There is no controls. We had no control group. We don't know. Can you assume that correlation just because employment went up after the tax cut, can you assume that the tax cut was the cause? Some people would, probably Republicans would. Democrats would deny it, but we just don't know. Got a couple of really interesting ones here. I hope you can see this if you're looking at this online. Purple is the rate of autism. Red is organic food sales. Do we really, honestly, and truly think as the years go by, as the number of food sales goes up that are organic, does that increase the number of autism cases? I would surely hope not. Okay? But if you're going to say that the Bush tax cut caused employment to go up, you would almost have to agree that organic food sales caused autism cases to increase, which is rather ludicrous. Another one, here you have the highway fatality rate. And here we have lemons imported to the US from Mexico, for crying out loud. As the years go on, you see how the highway fatality rate is decreasing, right? As the number of lemons imported from Mexico increases. Do we really want to say that? I would hope not. It's very difficult to ascertain just because there's correlation. It's difficult to ascertain the cause. And so correlation does not necessarily mean causation. One last one, and I'll give it up on this. Here we have obesity as a percentage of adult population. Okay, the number of obese people in blue, and the red is the total credit market debt as a percent of GDP. What? Do we really think as our credit market debt increased as a percentage of GDP that caused obesity to go up? I mean, you just cannot do it. Cannot do it. Oh, what is this? This is an interesting one. A statistic stated that the rate of teenage pregnancy in a conservative religious group was higher than the national average. What a scandal. A conservative religious group having a higher rate of teenage pregnancy? Well, if the truth be known, it wasn't a higher percentage of unwed mothers, it was a higher percentage of women who in this group got married while still in their teens, and then they got pregnant. All right? Oh yes, love misleading statistics. Not too many more. How about this one? Recent presidential election campaign, the challenger claimed that employment was up during the president's term in office, and the president claimed that unemployment was up. The challenger claimed that unemployment was up, whereas the president campaigned and said that employment was up. It can't be both ways, right? or can it? It turns out that both were true. The population had increased. It turned out that the number of people who were employed and the number of people who were unemployed had both increased. Don't you just love statistics? Okay, here's one of my all-time favorites. This was at the recent Olympics in Rio, 2016. It was just recently. Statisticians discovered something extremely interesting. On the Olympic pool, you've got 8 lanes. Here are the starting blocks. Okay? They found out that when people were doing the 50-meter freestyle, that's one length through the pool, one length, that people in the lower numbered lanes had faster than normal times than people in the upper lanes whose times were slower than normal. What is going on? They discovered that there was some sort of a circular current in the water at the swimming pool at Rio. And when you were swimming this way, the current helped to push you, whereas when you were swimming in these upper lanes, it held you back. Now, if you are swimming like 100 meters or 200 meters or 1,500 meters, whatever, if you're going up, back and forth, there's no advantage because it may help you a little on the way up, but it's going to hurt you on the way back. Here, it's going to hurt you it's going to help you on the way back and hurt you on the way down, okay? But in the 50 meters, statisticians figured it out. Something was funky about the Rio swimming pool. I just thought that was really fascinating. Okay, so we're going to wrap up chapter 2 talking about distribution shapes and different things we can do here. We talked about pie graphs, bar graphs, dot plots, stem and leaf. But the best thing you can do is to use a curve. You'll see at the top of page 72, if you want to turn there. Top of page 72, we have taken a histogram. I think, if I'm not mistaken, that these are heights of college, the girls at a Midwestern college. These are their heights, okay, in inches. And if you connect all of the bars, you can see that if you connect them all, you get this nice, smooth curve. All right? Down at the bottom of page 72, we're going to have a whole bunch more shapes that we're going to need to talk about. But first, before we get down to the bottom of page 72, bell-shaped curve for these 3,000 female students at the university is a bell-shaped curve. It's called bell-shaped because it looks like the side view of a bell, okay? Either bell-shaped or normal. We call it a normal curve also. What about other examples of bell-shaped curves? How about shoe size, okay? If I looked at shoe sizes of women, okay? You're going to have some people with smaller shoe sizes. Now I'm talking about women, not all females, women. Let's say 21 and older. You're going to have small shoe sizes, you're going to have medium size, and you're going to have people with big feet. You're going to have bell-shaped curve. How about if we did IQs? We already talked about this before. You're going to have some people with lower IQ, some people in the middle, a larger group in the middle, and some people out on the other side with a higher IQ, bell-shaped curves, okay? So if you look down at the bottom, all the different kinds of shapes. Bell shape is listed first. You have triangular, uniform, J-shaped curves, right skewed, left skewed, bimodal, multimodal. We're going to talk about most of these shapes today and the impact it's going to have on this course. Okay, distribution of a set of data is the table, graph, etc. that provides the value of the data and how often they occur. A graph with one peak is unimodal. That's one mode. Mode is the number that's repeated most often, if you recall. Bimodal has 2. Multimodal has 3 or more peaks. Remember, mode is the one used most often. Skewness. Easy way to remember skewness. Right skewed means that the graph is asymptotic with the x-axis in the positive direction to the right. So a right-skewed graph gets closer and closer and closer to the x-axis in the right-hand direction. Closer and closer, that's what the word asymptotic means, okay? Now, here's an example of some different kind of distribution shapes. Pakistanis were asked about their interest in learning a foreign language. And it appears as though there's almost two peaks. The 20 to 25 group here, possibly you can't see this if you're doing this online, and the 30 to 35 group. It looks like we have two peaks. A great name for that would be bimodal. Here's some examples that I thought of for bimodal shapes. The heights of 1,000 men and 1,000 women. If you mix them all together, you're going to have a curve for the women, and you're going to have a curve for the men, okay? And you're going to have peak for the women and a peak for the men, because men are a little taller than most women, okay? So that would probably be a bimodal. How about the price of books on my wish list? If you compare paperback versus hardcover, the hardcovers are going to be a little bit more expensive than the paperbacks. Family income in the United States. Unfortunately, we are kind of lately dividing into two groups in the United States. There's a higher income group and a lower income group, okay? And you're going to have a bell-shaped curve for the lower, a bell-shaped curve for the upper, and you're going to have two peaks. As I said, unfortunately. Here is a distribution that would be right skewed. Teens were asked questions about parental encouragement. Right skewed, it goes up, and then it looks like it gets closer and closer to the x-axis, okay? You know, in a way, it's kind of bell-shaped also, okay? It's kind of bell-shaped. How about right and left skewed? It's kind of tricky to come up with some examples for left skewed, but how about right skewed? Cost of a house. Don't most of us live in homes that would have a peak at the lower price of the house, but you're going to have some richer people, right? So you're going to have, most of us, okay, are going to have relatively cheaper homes, and then you're going to have richer folks way out here, not as many, okay, who live in a much pricier neighborhood. How about the number of kids in a family? We're going to do something on this vein a little bit later in our time together today. Would look similar to this. Most of us have smaller families, but there are some large families, okay? And the only difference with families as compared to cost in the house, the number of people and kids in a family could start at 0, whereas the price of a house usually does not start at 0. All right, left skewed, I thought were a little trickier to do. Left skewed would look like this, okay? How about disposable income in the hands of students at Harvard? Okay, I'm assuming that people that go to Harvard are probably wealthier, would have more disposable income over here, all right? Number of applications submitted by MBA grads before you get a job. Oh, you've got to submit quite a few before you get a job, and the average actual number, did my research on that, is actually 9 to 13 applications. How about that? Some more shapes. This is an example of a J shape. Okay, now I agree it is skewed to the left. Okay, but the thing you want to be careful about is this is a J shape. J shapes will always be skewed to the left. Okay, because the letter J comes this way, right? J shape would always be skewed to the left, but not all left skewed are J shapes. Okay, that's something you got to be very careful about. Just because it is left skewed does not mean it's a J shape. It could, left skewed could come up and then bend, right? So you got to be careful about that. because J-shapes are monotonic, which means they always either increase or decrease. All right. How about the number of fingers on the hands of a randomly selected person is which J-shape? I mean, if you're thinking about the number of fingers on the hand, you're either going to have 0 fingers, I would hope not, 1 and the whole way up to 5. Yeah? Are you with me? So there's going to be very, very few people, okay, that are going to have 0 fingers, okay? But then it would increase, and the vast majority would be up at 5. Wouldn't that be a regular J shape? 1,000 people are selected at birth. What J shape gives the number of people alive after X years? If this is years, you're starting with 1,000 and it's going down, right? Monotonic, okay? Skewed to the right, that would be a reverse J. Risk of death as cigarette consumption or cigarette use increases. If the cigarette, these maybe could be packs per day smoked. What's going to have the risk of death? Going to go up uniformly. That would be a regular J shape. Okay. Now, what about rectangular or uniform shapes? Okay. You toss a die 1,000 times and record the number of 1s, 2s, 3s, and so on. There's 6 sides on a die. If you do it 1,000 times, things are going to even out. You're going to get the same number of 1s as 2s as 3s as 4s, 5s, and 6s. 6 into 1,000, what about 167, right? You're going to have about 167 of each one. That should be rectangular or uniform. Or what about if you do 1,000 people and record which day of the week they were born? 1,000 people, it should average out. 7 into 1,000, can I do that in my head? Would be 1, 4, 2, right around 142 people each day of the week. Okay? Uniform, rectangular. So, a couple of comments now to kind of wrap this up. Data for a sample is not the same as the data for the population, but it should be similar in nature. Okay? It should be similar. All right? And the bigger the sample you pick from the population should be closer to being what the population graph is. All right? We're going to do an example of that today. Similarly, the distribution graph of a sample is not the same as the distribution graph of a population, but it should be close. If you're doing randomly sampling, representative samples, okay, doing everything randomly, it should be very close. Remember the Perry County study where they were picking people at employment centers and senior citizens' homes? That was nuts. You got to pick your survey randomly. Looking at the graphs on page 75, if you want to look there with me. Page 75. The population distribution is up at the top of the page in blue. And then they ran 6 different samples. Okay? They ran 6 different smaller groups of the population. Look at all 6 of the brown ones. They are reasonably close to the blue. Are they exact? No, but they should be reasonably close. You get better and better approximations the larger the sample. Now, here's what we want to do to test this. If I'm teaching this in a classroom, I'm going to go through and determine the number of siblings per student. Okay, we'll construct a relative frequency histogram, single value. Then we're going to get a sample of 1/3 of the people in the class. Okay, do a relative frequency histogram for the sample and look at the 2 bar graphs, and they should correspond. Now, because this is online, and I'm assuming you're not in class, all right? So I've got a table that I've constructed for 30 people and the number of siblings in their family, okay? So what we want to do is a relative frequency histogram for this data. So the first thing you're going to do, you can see that we have how many children in a family? Anywhere from 0 up to 4. Okay, so you want to do 0 okay? You want to pick out, like for instance, how many zeros are there? 1, 2, 3, 4, 5, 6. Let's do it again. 1, 2, 3, 4, 5, 6. So there's 6 that have 0 kids. This is the number of kids in the family. This is the number of families that have that many. You're going to then, once you get this done, okay, and there's a total, should total up to 30, you do relative percentages. 6 divided by 30 is 20%. And you're going to make a histogram for 0 should go up to 20%. Are everybody with me? Okay? All right? Then, what I want, once you get your histogram done for this whole data, from 0 through 4, kids in a family, okay? Now I want to pick out a sample of these 30. A sample of these 30, okay? I'm going to erase this. Let's pick out a sample. Now, what I did ahead of time to make it easier for you, I went to the random number chart on page 13 in your textbook. I randomly picked line number 5 in columns, sorry, I misspelled columns, and columns 8 and 9. I then went down the column, up, down, up, until I selected 10 randomly selected people, okay? I picked people between 1 and 30. If I picked anybody twice, like I think 27 appeared twice, I went on to another one. I wanted to get different people, okay? We're not replacing, all right? So here are my 10 randomly selected people. So what are the 10 randomly selected people? I've got number 10, which is, right here's number 10. Person number 10. I have person number 8 here. I have person number 1 here. Here's person number 1. Person number 4, see what I'm doing? Person number 27. Person number 18. 18. Person number 11. Person number 3. 28. And person number 15. That should be 10. 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I've got 10 people. Now, that's my sample. Now I want you to do the same thing. 0 kids, number of kids, 1, 2, 3, or 4. How many in your sample had 0 kids in the family? 0 siblings. 0 kids or 0 siblings. We're doing 0 siblings of the people. Okay, so 0 would be, here's 1, 2. Is that it? 1, 2. So I've got 2 with 0. How many with 1? Here's 1, 2, 3. I think that's it. 1, 2, 3. Okay, right? Then this should come up to be a total of 10, right? 2 out of 10 is 20% for your first bar when you make your histogram for your sample. Are you with me? Okay. So, and then what you want to do is compare the bar graph with your first, with the whole data, the first bar graph that I erased up here. You want to compare it to this bar graph. They should look reasonably close to being the same. Okay. It's a great exercise. Don't you just love statistics? Super stuff. All right, so you have your sibling study to finish, and then you have some problems in the text. Enjoy, enjoy. Next time, we will be reviewing and getting ready for a test.